Okay, it's a pleasure to welcome Julianna Tymoczko from Smith College, and she'll talk about splines, equivariant cohomology, and applied mathematics. Please, Julianna.
Okay, thank you. Do I have audio? Am I adequately mic'd? Okay. So there's various funding organizations that have supported different parts of this work, but I just gave up on listing all of the people who have participated or created the thoughts here. So I'm going to try to say all of the names as we go, and also say plus other people at various points. And I'm also, well, okay. And also, I think, assuming that it is Monday and before lunch. So I'm going to give a little bit of a review of some of the things Michaela was talking about at the beginning of the day, some of the torus equivariant cohomology and GKM theory, but also with an eye towards which pieces I'm going to generalize and which pieces are specific to this one particular way of thinking about what I'm going to end up calling splines. So the second part will be talking more about like splines and comparing some of the things that we think about in this sort of context of this conference versus another sort of conference. And then three, we will talk about some questions, though some other ones will come up as we go. Okay, so the setup, again, we've got some sort of suitable geometric object with a well-behaved torus action. There's various different ways you can like say what any of these adjectives mean, but some of the things that are most commonly used in this setting: symplectic manifold with a Hamiltonian T action, smooth, complete, complex toric variety, partial flag variety G mod P with its sort of maximal torus acting on it. There's other kinds of things we could say, but this part is a vibes thing, right? So the torus is acting on X, and as we were hearing before, the pieces that I think are important here are isolated fixed points. The boundary of each one orbit consists of two distinct fixed points, and this additional condition called equivariant formality, which I will get back to there. Okay, so this is just a little asterisk. So necessary, they're sort of like two different things that are going to go into the theorem that we're going to talk about. So when I say necessary, it's to get a certain kind of combinatorial operation working. But if what you want is to compute equivariant cohomology, then you can do other things also. And so you know, people get this this package to work without all of these conditions. So here's some places where I could put names like Gilman and Holm and Braden and Chen Sotili and many other people, some of whom are in this room. So again, here's the picture. We have a bunch of fixed points that are isolated. They are being included into a larger variety. So we get a map from the equivariant cohomology into the equivariant cohomology of the fixed points. And in this room, it's often called the localization map, and that confuses people if you go into other places. So I'm not going to call it anything. So sometimes this map is injective. Even more sometimes you can identify the image, and then GKM is sort of just like delineating a little set of conditions that say this image really is coming from a particular kind of combinatorial graph theoretic operation. So here's another place where I could list a whole lot of names. I guess I didn't say Goreski, Kotwitz, McPherson either, but that's the GKM. Attia and Kerwin and many other people, and this sort of whole philosophy. This is like a philosophy as well as a set of results. But let's go to the GKM graph. or moment graph, since we have isolated fixed points, I can create like just a combinatorial graph. Vertices are the fixed points. Since the edges come with some fixed points, just 2 of them in the closure, I have a nice way of creating edges. And so these I think of as these one-dimensional T orbits. So here are some particular examples. So here's flag variety for SL3, which we saw earlier. Here's this particular regular semi-simple Hessenberg variety that we also saw earlier. And here, that little square there is like a P1 cross P1. So different ways of making this work. And then in addition, our edges have a label, and that label is the weight of the torus orbit. So over here for these leftmost examples, we've got I represent the labels just with a color so the document doesn't get too messy, but blue is T1 minus T2, and red is T2 minus T3, and green is T1 minus T3. And then over there, we've got, I don't know, something alpha and beta on the 2 different directions of P1. And then recall. So for a single point, we've got the equivariant cohomology of the point is a polynomial ring. And I'm going to just say complex everywhere because I'm happiest that way. But if you wanted to, you could say stuff without using complex. And this all means that this image of this map is sitting inside of a bunch of copies of the polynomial ring, 1 for each fixed point, or if you're thinking about it from the perspective of the graph, 1 for each vertex of the graph. All right, and so here's what I will be calling the GKM condition. We are going to think about the elements, so tuples of polynomials, 1 for each of these fixed points or vertices, and then we're going to look over each of the edge and require that the difference between polynomials on either sides of the edge is a multiple of the label on that edge. So, so the GKM theorem says these collections of polynomials form the image of this map, like that is the thing that is the image of the map. Okay, so then, yeah. Okay, so then first off, what we're doing here is we're identifying the equivariant cohomology with a particular subring and submodule of these tuples of polynomials using pointwise multiplication, addition, scaling, everything is like pointwise. Second off, again, this sort of like condition equivariant formality. So I think if you are a topologist or if you are interested in a particular geometric object and you're like, oh, I want to like use some of this apparatus, then you care a lot about equivariant formality. But I'm going to stress the following. Could be a definition of equivariant formality depending on who you are, but the equivariant cohomology of X is a free module over the equivariant cohomology of a point. So like the word free. Yeah. So it's for a lot of, so the question was, is it important that I use complex numbers instead of like Z? Sorry. Yeah. So I translate to American there. No, it's not. So is it important? It is important for the result as stated by GKM that you at least use rationals, but it's not particularly important that it be complex. And in many examples or specific cases, you can use integers and in, you know, like, but so I think I would say it's no, I mean, but sometimes, but you're like not complex for sure. But the integers in particular can be fussy. All right. So then here's the framework. And actually, if I had been 100% aware of which slide was coming next, I would have said that question was a great segue, because part of the answer to the question, is it important that you're using the complex numbers rather than the integers, is like, well, is what do you want to do? Like, so what do you want to do with this? And part of what goes into the GKM theorem is there's one piece, which is a topological statement. Here's a class of varieties, and this is what their equivariant cohomology is. And then there's another piece, which is an algebro-combinatorial statement, which is here's a particular combinatorially defined ring and module that you can do stuff with. And here are some circumstances under which these two rings are the same, right? So, so the framework for splines is actually any ring. I'll say commutative with identity because otherwise my head will explode. Any graph, just vertices and edges. And I want the edges to be labeled with ideals in the ring. So each edge has an ideal on it. So then what the GKM condition is doing is it's defining both a subring and an R submodule of the collection of elements of the ring, one for each vertex. So splines on the edge labeled graph that you have been given with coefficients in R are, they'll use this notation roughly, but we're just going to do the same operation. We're going to put an element of the ring on each of the vertices. And there's my GKM condition, just copy pasted, so that the difference between two ring elements on opposite sides of an edge are a multiple of whatever label that you've put on the edge. And we're going to do this just over all of the edges. So again, back to this question, is C important? I mean, you can just change everything from complex numbers to anything you want and ask this question of like, which things are in this ring? And does it actually correspond to some meaningful object out in the geometry topology world? Well, that's a separate question. And can you compute with it or do whatever algebraic process you want? Well, that's also a separate question, but you can do it always, right? So there's our sort of first kind of example. It was like everything that we were saying about GKM graphs. If you think about your edge label as the principal ideal, so just whatever that sort of torus weight is, I'm going to take the ideal that's all multiples of that thing. And then the polynomial ring, so the coefficients here is this polynomial ring, equivariant cohomology of a point. Then what we're saying is the splines are the image of the equivariant cohomology, and the collection of spaces that GKM identified is like nicely delineated so that actually that localization map is an isomorphism onto this image. Yet the splines are always sitting there inside the image, always. So classical splines, or like if you Google splines or talk to an analyst or something, classical splines are piecewise polynomials on some polyhedral decomposition of space that satisfy some kind of K differentiability constraint. So here's an example. This is a triangulation of a triangle in the plane. And those are the particular lines, x equals 0 or the y-axis, and y equals 0 or the x-axis, and a fragment of the line y equals x. And then I have those three polynomials. And I'm giving these K differentiability constraints on one particular pair of polynomials, but I actually want it to exist all around. So restricting to their mutual intersections, the polynomials are the same and the derivatives are the same, and so on up to the k-fold derivative. So that condition, the K differentiability condition, is determining which ideal you are looking at. Let me say a couple words. So here I've got like x-axis partitioned by the point x equals 0. So these are single variable polynomials. I've got 2 of them. So if they agree at the point x equals 0, like that's true if and only if their difference restricted to the origin is 0, if and only if you plug in 0, the difference is 0, which is to say, if and only if their difference is sitting inside of the ideal generated by x. So, okay. On the other hand, if the first derivative agrees at x equals 0, then same kind of argument, if and only if the difference between first derivatives at 0 is 0, which is to say x squared divides the difference between the polynomials. And right, so on and so forth. If they agree and are k-fold differentiable on the intersection, then x to the k plus 1 divides the difference of the 2 polynomials on either side. So, in other words, and generally, sort of like I think the analysts and especially applied mathematicians, they care about like specific families of things that they're doing, rather than necessarily a question like, for which families of objects does this theory work? So I don't know, like this is my way of saying, if you go and look, at how they frame this, it's usually in terms of a specific family of planar triangulations or particular kinds, or even particular kinds of polyhedral decompositions of particular kinds of objects. It's sort of like the most general statement. But this is kind of basically the idea. You've got some polyhedral decomposition, you've got 2 facets, so maximal dimension faces. Their intersection is characterized by some kind of codimension 1 object with some like affine linear form. So it can have a constant, and then all variables are degree 1. So then you have 2 piecewise k differentiable polynomials in this facet. Here they are being divided by that codimension 1 object, and there's the 2 faces, and there's my 2 polynomials. So this condition holds if and only if in the dual graph, where I put a vertex for each facet and I put an edge between them, if the 2 facets intersect in a codimension 1 piece, so then the polynomials labeling those vertices should differ by a multiple of L raised to the k plus 1 power. Yes.
In the case of a simplicial complex,
yes.
The Stanley Reisman.
Yes. 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 And yes. And I guess. Sorry. So yes. Actually, one of the people. So Lou Valera, I think. Yeah, Lou Valera sort of, as far as I know, it's like the first person who like kind of really goes through this process of thinking about analytic splines, and it's like, well, it's the same thing as doing a process like this on the dual graph, and then furthermore also says that like so it is possible to come up with examples of simplicial complexes for which the dual graph is not in fact exactly the same, but it would involve doing weird things that we don't generally do. I mean, so we basically never do in geometric, topological, or analytic applications, and that are kind of like hard to get to if you're doing algebra and combinatorial manipulations. Like, so no holes in things. And so, okay, so then I just want to like highlight, so there's many similarities between these examples. Oh, and actually related to that, so Champagne actually constructed equivariant cohomology of toric varieties directly using the sort of perspective, the spline perspective of piecewise polynomials, using that also to show it's the equivariant Chow ring and that it's equivalent to several other objects, right? So those two sort of perspectives of the dual graph and the dual polyhedral simplicial object are both in sort of both topology and analysis literature. So let me highlight some of the differences between the examples. One is the edge label, and generally it's just the weight of a torus action, L, in the sort of toric topology kind of context, whereas in analysis it is just always possible and it's largely speaking always interesting to think about raising it to any power. So because of that little k+1 there, the thing that we think of in the sort of GKM graph setting is the zero differentiability condition. Yes, k greater than or equal to 0. 0 is allowed. I actually proofread for exactly that point and got it wrong. Okay, so degree. Here's actually another thing. Generally, we are always thinking about degree being infinity in the sense that I am allowing my class to have any possible degree. And if I want to care about only some finite number of those things, then I'll be like, well, I've got a graded ring and I'm going to restrict to this part of the graded ring, right? Generally in analysis, they go the opposite direction. They will always restrict to degree less than or equal to D. And one reason why they do that is because then they end up with a finite vector space. So they usually want to use the real numbers, they would not like to use the complex numbers, but they wouldn't like to use the integers either, because they want full-on vector space. So that would be another piece. Third, yeah, so free. This is kind of built into the apparatus generally, and it is not in the analytic situation, and that is honestly confusing. Yeah. No, this is right. That's not a double R. That's not mathfrak. That's just any old ring. Yeah.
So the small comment about the last one. So for toric varieties, for example, this piecewise polynomial view was also a lot pushed by Michel Briand, and you can do it on any fan, and if you don't have complete or whatever, so it may then be not free, but it's still this piecewise polynomials will give the equivariant cohomology of the possibly non-compact but smooth toric variety. And then related question and sort of to the first entry. So you said in toric topology, or like in topology, you always take L to the power 1, right? And a question to you or to everybody here is, if I took higher powers, like in the analysis column, right? Is there any way to relate the resulting ring to topology? Is there some kind of special cohomology or whatever?
So I feel some chagrin, like when I'm teaching and say a joke and somebody in the class says the punchline. So I have a slide in about, we'll get there in about 5. Yes, this is excellent question, kind of very clear and natural question, right? Does this mean anything? Does this mean anything to us? So I guess well, we'll go to, when I get to the slide, I'll say more stuff, but yeah, right. So I want to show, so I want to show an example of non-freeness. This is not that example. So this is an example of the graph P1 cross P1. The labels are going to be squared. And I'm going to represent my splines just by drawing the graph and ticking some labels on the vertices. So here's a set of free generators. And I think of constructing them sort of just as I might construct an upper triangular basis, sometimes called like a flow up set of generators. And in the toric case, right, so you have, if you have a torus action, then you have some kind of flow that you can use to just sort of push things away and have some sort of geometric reason to believe and know that these generators exist. And furthermore, to say something about the kind of lowest non-zero polynomial that you see there, right? Like the further you get out into the graph, you might have less to say, but you have some information at the beginning. Yeah, because I was just seeing if I could make a point from this thing. Okay, but here is a different sort of example. This from a problem in splines that we'll also, I think, return to. So again, sort of thinking of it as upper triangular generators, those we've got the identity spline over there and that same x squared 0, 0. But then somehow the next step up, I would like to put in 3 zeros, at which point I need a degree 4 spline if I'm just going to stick 3 zeros on the vertices. However, here's 2 degree 3 splines. I would normally want to be like, just trust me, they're true. Now I'm like, well, I missed that greater than 0 thing, so maybe we should just like not look at it very carefully at all. And it's probably pretty close to true. So these things down at the bottom, just in case you'd like to confirm a little bit, I originally wrote my polynomials here at the vertices so that you can see it satisfies spline conditions, at least on the blue edge. But if you multiply it out, you can see it satisfies spline conditions moving up. And here's the sort of calculation whereby you can kind of see that there's relations amongst these generators. So, right, from the analytic splines perspective, this is sort of the thing that common, this is more normal. This is the common phenomenon, not really the unusual phenomenon. So just some things we can do with splines, like the idea of taking subgraphs, like you naturally have this restriction, but you can like, so that was the irregular semi-simple Hessenberg variety, which is very nice and well behaved. But you can erase any edges you want, including silly edges, and still get perfectly good splines. You can do certain kinds of path replacements, right? So here's something like the path from U to V, and the ideals labeling those edges. So I can just replace that with an edge from U to V, modify the ideal, and have a way of sort of comparing and analyzing splines with a simpler combinatorial picture, where I've like sort of shoved some of the complications into the algebra. Also something that doesn't sort of naturally easily show up in a kind of GKM setting. We can change coefficients. So there's some of the examples that we were talking about before, but also like you can use quotient rings. So some of the things, so like for instance, a kind of upper triangular calculation of module generators is possible, but gets more subtle if your coefficients are a domain, because you can get up to the top of a cycle and have a product of things that suddenly becomes 0. And then sort of the point here is anything that you can do on a graph with this algebraic package, you can just do. And this sort of question of does it have a geometric interpretation is often interesting, but also like not necessary if you're trying to answer questions like how many generators are there, or like what is the dimension of this space, or other things like that. Okay, so right, his question. So the splines on the very far left are the ordinary equivariant cohomology. And then as you move to the right, what's going on? Back to Matthias's question. And it's super interesting. I like I don't have much to say here. I guess the one thing that I might add is that yeah, so sorry, like now that I'm like in front of everybody and on Zoom in front, this is going to be recorded for posterity. I'm like, I believe it is possible actually to create splines further down on the right with like higher powers that are not actually splines in the original ring. But now that I'm in front of everybody, I'm like, I should just erase that thought because yeah, that's so anyway, yes, we'll just like go on with this and say this is an interesting example of something that the sort of applied mathematicians bring to us. Oh, they would always use the same K on every edge. We could, I mean, like, I don't even know what this means. So like, yeah, yeah, they definitely would always. I guess that goes back to this question of like, if you think of the edge labels as ideals, then you pick your ideals. So then question of can we analyze spline representations? So so I've like sort of modified some slides based on this morning. But right, I'd say like any graph automorphism that preserves the GKM conditions induces a representation on the module of splines. Like that's the fundamental thing that you need to do. So here is the morning talk, regular semi-simple. Hessenberg varieties, here's one way of sort of writing the definition of the action that we saw. So acting on a spline or a class means both moving the vertex labels and acting on the polynomials. And back to Yael's question earlier, like it preserves the GKM condition at each edge and therefore like acts on the entire module, right? But so for flag varieties, here's another example. Here you just act on the right. So you just permute the polynomials acting on the right. You don't really do anything to the actual variables inside each polynomial. And it's still preserving the, so here I sort of flipped these two and these two and those two up there. But it still preserves the GKM conditions edgewise. So it's still a perfectly good spline representation. And really sort of generally, again, any action that makes combinatorial sense, you can do. So like, here's something with a, significant lack of symmetry, but I can still exchange horizontally and get an S2 action on this collection of splines. And so this particular example, great, yeah. Okay, so this particular example, I pull out because of the upper bound conjecture. So here, looking at splines on graphs dual to planar triangulations. So restricting to degree at most 3 and differentiability 1. So the labels are all going to be squares. The upper bound conjecture is a formula for the dimension of the spline space as a vector space. In the context of a sort of GKM setting, basically this formula, you can translate it through the dual graph mechanism into sort of spline graphs, and it's roughly going to predict the number of R module generators. And it basically is saying we've got 1 plus a certain quantity adding up over the faces, and then another like modifying quantity for non-singular faces. And here's sort of what that's meaning, that 1 is the constant spline, which you then remove from everything. And then you have your sort of non-constant generators of degree less than or equal to 3, and that sort of moves around all of the faces. And then you have this like correction factor. And the correction factor is showing up precisely for the faces that have symmetry. So exactly these 4 cycles with symmetry, which we actually showed earlier. So the degree less than or equal to 3 module generators, if you have symmetry, there's 3 of them. And if you don't have symmetry, there's 4 of them, 2 of which are the non-free generators. So this is sort of like a quite vexing and fairly longstanding conjecture. Vexing also because it seems like it should be solvable. But also appears to be using some kind of like, or relying on some kind of underlying symmetry in sort of portions, just portions of the underlying graph of splines. And let's see, I guess I'll just stop at this point. Thank you.